In this video, we'll talk about Hess's law and the combination of various thermochemical equations to come up with other equations. As an example of how Hess's law can be applied to the process of determining the enthalpy for a reaction, we see here the reaction of elemental carbon in the form of graphite reacting with hydrogen and oxygen to form carbon dioxide and water, which is a very exothermic process, releasing approximately 2,148 kilojoules for every 3 moles of carbon that is consumed. If instead of going directly from the elemental carbon and hydrogen and oxygen down to the products of carbon dioxide and water, we take a series of reactions and combine the various enthalpies for each of the steps, we might discover another way to come up with the overall enthalpy of this reaction. So, turns out that we could take the carbon and hydrogen and oxygen and combine them to form 3 carbon dioxides, and also then consume some of the oxygen and producing 3 carbon dioxides, 4 hydrogens, but now 2 oxygens. And then if we do another step, we could then ultimately end up with our products of 3 carbon dioxides and 4 waters. It turns out that the enthalpy for the first step of this reaction is exothermic by 1,181 kilojoules, with the formation of 3 moles of carbon dioxide. And the second step is also exothermic by 967 kilojoules. If we add those together, we come up with our total process, which turns out to be pretty much the same as what we observed previously. Turns out that we could do the same overall process in a different way if we were to take propane, C3H8, and consume some of the propane and do the combustion reaction. We would go down to our products, but we could also remove some of the hydrogen and go to the graphite in an endothermic process, which is the blue arrow going up. If we look at the enthalpy for the process of taking propane to graphite, you see this is an endothermic process of 105 kilojoules. However, if we were to do the combustion and go down to the carbon dioxide and water, this is exothermic by 2,043 kilojoules. You'll notice then that if we change the sign of the process for the conversion of propane into graphite and do the reverse process, that would be an exothermic process. And then if we combine that with the combustion of the propane, we come up with our overall process, which is negative 2,148 kilojoules. So in fact, there are 2 separate ways that we can come up with the overall reaction of taking graphite and turning it into carbon dioxide and water. So we can draw some conclusions from this, and that is that if we are interested in the enthalpy of an overall process that can be broken up into several individual reactions, the overall enthalpy has to be the sum of the enthalpy of each of the steps. So if we are interested in the enthalpy for the reaction in which methane reacts with elemental oxygen to produce gaseous CO2, but also then forms liquid water, as you see here. We can break this up into two steps by first knowing the enthalpy of the combustion of methane to produce CO2 and gaseous water, and this is an exothermic process of negative 802 kilojoules. But then we can also have the water in the gas phase become liquid water. This is a physical reaction, but this is also an exothermic process. The gaseous water would have to have some heat removed from it. So in this case, 44 kilojoules for every 1 mole of the water. And since we would have to have 2 moles of water from the previous reaction, we would have to double that, and that means we would have to double the enthalpy for the second reaction. If we then cancel the gaseous water molecules that appear on both sides of those reactions and add them together, leaving out the water in the gas phase, we come up with our desired overall reaction. And so therefore, if we add together our enthalpies, we come up with the overall delta H for this reaction of negative 890 kilojoules. As another example, we could determine the enthalpy of reaction between aluminum metal in the solid state reacting with manganese 4 oxide to produce aluminum oxide and manganese metal. We can break this up into two reactions. The first is the formation of aluminum oxide from elemental aluminum and oxygen, the balanced reaction forming 1 mole of aluminum is shown here, or aluminum oxide is shown here. This is an exothermic process of negative 1,676 kilojoules. Likewise, we have the reaction of manganese metal and oxygen to form 1 mole of manganese 4 oxide. This is also exothermic by negative 521 kilojoules. And so if we were to then take our first reaction, we see that in order to have the right number of moles of aluminum oxide, as you see in the first reaction, we need 2 moles of aluminum oxide, so we would have to double that reaction. That also means we'll double the enthalpy. The second reaction needs to be reversed so that the manganese 4 oxide is a reactant and the manganese metal and oxygen are products. And so in this case, we also need 3 moles of the manganese metal, and of course by reversing the reaction we need to change the sign of the enthalpy. So if we multiply that by negative 1, then we multiply by our 3 to get the stoichiometric relationship right, and then we're going to combine these two reactions and canceling out the moles of the oxygen. And turns out that when you do that, you end up with the same reaction you have in the first reaction. Therefore, we can add together our enthalpies, and this then gives us the overall enthalpy of this reaction, which is negative 1,789 kilojoules. So, the balanced overall thermochemical equation can be written as the balanced reaction plus the enthalpy associated with it. A related topic is the bond dissociation energy. This is the enthalpy associated with breaking a bond and forming isolated atoms in the gas phase. As an example of this, we take elemental chlorine in the gas phase and add energy to this. It would produce 2 isolated chlorine atoms in the gas phase. And so When more than one of the bonds are broken, we're going to have to take into account the fraction of the enthalpy that is used. And so, for example, if we took methane and turned that into isolated carbon atoms and hydrogen atoms in the gas phase, we have broken 4 CH bonds. The reaction it requires 1,656 kilojoules of energy to break all 4 of the bonds. Therefore, we would need to divide that by 4 to get the bond energy of an individual CH bond. So, it turns out that bond energies are often positive. We have to put energy in to break a bond, but in some cases they can be negative. Shown here is a table of typical bond energies in kilojoules per mole. You'll notice that on the left-hand side we have things like carbon bonded to other elements with single bonds. They have a range of energies, but are typically lower in energy than, say, a carbon-carbon double bond, which is over on the right-hand side here, and then again lower than a triple bond. As an example of this, we would like to determine the enthalpy change for the combustion of 1 mole of ethene, which is C2H4, and so we are going to determine the enthalpy for the reaction using bond energies. So, in this case, the overall reaction is C2H4 plus 3 elemental oxygens to form 2 carbon dioxides and 2 waters, all in the gas phase. In this case, the first thing that we should do is determine the Lewis dot structures for each of the reactants and products so that we know exactly what kinds of bonds we're dealing with here. And so you see that ethene has 4 carbon-hydrogen single bonds and 1 carbon-carbon double bond. Likewise, for the elemental oxygen, we have 3 O2 molecules, and the Lewis dot structure has an oxygen double bond. The products, carbon dioxide, an individual carbon dioxide molecule has 2 carbon-oxygen double bonds. And then our other product, water, has 2 oxygen-hydrogen single bonds. If we then go ahead and determine the number of each of the types of bonds for this overall reaction, remembering that the equation is the sum of the bonds that are being broken and their bond energies, subtracting away the bond energies for the bonds that are being formed. So if we were to determine from our table the bonds that are being broken on the reactant side, we're breaking a carbon double bond, which is worth 611 kilojoules per mole. We're breaking carbon-hydrogen bonds, which are 414, and we're breaking oxygen-oxygen double bonds, which are 498. On the other side, we're forming OH bonds, which are 464, carbon-oxygen double bonds, which are 736, and in the CO2 molecule, the carbon-oxygen double bonds are slightly more energy, so we're going to be using the 799. All right, so we're going to sum these all together. We notice that the bonds that are being broken, we have 1 carbon-carbon double bond, 4 CH bonds, and 3 OO double bonds. And then we're going to be subtracting away the 4 carbon-oxygen double bonds and the 4 OH bonds. And so we plug in our numbers, noticing that if we use the CO double bond for the carbon dioxide of 799 on the bonds that are being formed rather than a typical CO double bond of 736. We add this all together and do the math, we should come up with a negative 1,291 kilojoules, and this should be the enthalpy for the overall reaction.